For the third question, determination of rate law, right, we're asked to, looking at the reaction of A reacting with 2B goes to C, we have to determine the rate law for this reaction. And to determine that, we have to look at the different rates at different concentrations. So if you'll notice between concentration 1 and 2, they double, between reaction 1 and 2, they double the concentration of B, 0.03 to 0.06. And then between trial 1 and trial 3, we double the concentration of A. So we're going to, by changing the concentration and then observing the rate of the reaction, we can get an idea of the contribution of A and B to this reaction. So for right now, right, when we go from trial 1 to 2, the concentration of B doubles, the rate changes. And if we look at trial 1 through 3, the concentration of A doubles, and again, the rate changes. So for now, we know that the rate of the reaction, it changes as A and B change. So rate equals K times the concentration of A times the concentration of B. Now we need to find the rate order, right? Those are the exponents up here for A and B to determine how much each of them contributes to the rate of the reaction. And so to do that, kind of the equation that I gave you in class is basically what's your final concentration divided by your initial concentration raised to an exponent, and that should equal your final rate of the two entries you're comparing divided by the initial rate from those entries. And so if we wanted to find out the contribution of A to this reaction, we'd have to look at entries 1 and 3, because these are the only two entries where the concentration of A is being varied. So for our final concentration, we have 0.6 molar, our initial is 0.3 molar, and this is for A, and this should equal, what's our final rate? Our final rate is 1.3 times 10 to the minus 2 molar per second, and our initial rate is 3.2 times 10 to the minus 3 molar per second. And so when we divide these two, right, molarity will cancel out, and molarity per second, molar per second will cancel out. And we should be left with, for A, two raised to what exponent equals, and if we divide these two, we should get 4. So we can see that the rate order for A, the concentration of A, would be second order, right? Because what do we need? What would X have to be in order to make this equation equal? X should equal 2. 2 squared equals 4. And then to look at the concentration of B and the effect that that has on the reaction, we would look at entries 1 and 2, because in entries 1 and 2, right, we're changing the concentration of B and the concentration of A is staying the same. So for B, we would have 0.06 divided by 0.03 raised to an exponent equals, our final rate would be 6.5 times 10 to the minus 3 molarity per second, and 3.2 times 10 to the minus 3 molar per second. And so again, we divide, units cancel, and we should get 2 raised to what exponent equals, when we divide these two together, that should also get to 2. So in this case, X equals 1. So that means for A, the reaction is second order with respect to A. And then for B, we found the exponent must equal 1, so the reaction is first order with respect to B. And when we put that together for our final rate law, that means rate equals the rate constant times the concentration of A squared, because the reaction is second order with respect to A, times the concentration of B to the first power. So to get that contribution from A and B to the reaction, what we had to do was look at, entries 1 and 3, where we changed the concentration of A, and what did we observe happen to the rate of the reaction? The rate got 4 times faster. And then to figure out what's the contribution of B, we had to do the exact opposite. We had to look at 2 cases where the concentration of B changed and A stayed the same, so that when we doubled the concentration of A, the rate doubled. So that's what you'll need to do to kind of figure out what's the rate order for different chemicals in a reaction. And so in this case, right, second order with respect to A and first order with respect to B.